Welcome to part 5 of topic 2 on atomic bonding in mate 210. We're going to focus now on the types of atomic bonds. We just learned about the energy and forces between two atoms when they bond. So now let's look at what kinds of bonds form. You should have learned about this already in chemistry, so the words like covalent bonding, metallic bonding, and ionic bonding should be pretty familiar to you. Let's get started. Before we get into the bonds themselves, let's look at some of the material properties that are dependent upon the types of bonds and how they vary from one type of material to another. So the first property we can look at is material ductility. Ductility is how much you can stretch a material permanently before it eventually breaks. As we can see, ceramics are very brittle. They have almost zero ductility. They're way down there where that yellow circle is. Metals have intermediate ductility. They can be fairly ductile, and you can bend them quite a bit before they break, but they will break eventually. And polymers are extremely ductile. Some polymers can be stretched up to 7 times their original length and still not break. So here we see the range of brittle materials, and that for the most part, ceramics fall into the brittle category, metals are just above the brittle, and polymers are greatly above the brittle category. Another property we could look at is material density. Again, what we see is that ceramics have a moderate or intermediate density. They're not the most dense materials, that's generally metals, but they're also not the lowest density, that's polymers. And lastly, we can look at conductivity. This is a little bit more complicated, but hopefully you'll get the idea. Materials that are near the top of the graph in conductivity are what we call conductors. So there we see the metals primarily. Materials near the bottom of the graph are considered insulators. And here we have a group of ceramics that are considered to be insulators, and all the polymers are considered to be insulators. In the middle is a small group of ceramic materials that we call semiconductors. They're sort of between a conductor and an insulator, and they have special properties that we'll talk about in topic 5. So what are the types of atomic bonds? Well, all bonds fall into one of two groups, either primary bonds or secondary bonds. Primary bonds are bonds between individual atoms, and secondary bonds are bonds between molecules. Sometimes secondary bonds are called intermolecular forces. Among the primary bonds are 3 types: metallic, covalent, and ionic. And among the secondary bonds is the most important one that we'll talk about, van der Waals forces. You may have also heard about hydrogen bonding and dipoles. You can read about those in your textbook, but we'll not focus on them here in the lecture. So let's first look at metallic bonding. And I like to think of metallic bonding as a form of communism. Basically, the idea is that every atom in the metal gives up one of its electrons to a large sea of free electrons. So as the picture shows, you have a metal cation in the center, that's the core or nucleus, and that's surrounded by a sea of free electrons that have been released by all these core cations. The electronegative charge between the negative electrons and the positive cores creates an attractive force between the electrons and the cores and holds the whole metal together. So there's really no single bond between any two atoms. Instead, there's a collective group of bonds going on simultaneously between all the electrons and all the cations. What this means is that the cations can pack together very tightly since the electrons take up no real space. They can easily occupy the gaps between the atoms. As a result, when the cations pack tightly together, the metal has high density, and that was one of the properties we saw before. So metals have high density because the atoms pack tightly together. Metals also have very good electrical conductivity, as we showed before, and the reason for this is the free electrons. If I apply a voltage to a piece of metal, the free electrons will travel from the negative pole of the voltage towards the positive pole. And they can do this very easily as they travel between the cations and along this regular lattice of atoms. Also, there's no directionality to metallic bonds. Directionality is a word we'll understand a little bit better in the next slides. But basically it means that there's no direction from that controls the bond from one atom to another atom. The bond can occur in any angle you'd like. So that means the atoms can slide past each other very easily. And this is why metals are usually very ductile. The atoms slide by one another much more easily than they do in other types of bonds. Now let's look at covalent bonding. And covalent bonding is kind of like socialism, where two atoms share electrons. It's formed by the sharing of two electrons between two or more atoms to establish stable octets in the valence shell of each atom. So for example, here we have two chlorine atoms. Each chlorine atom has 7 electrons in its outermost shell. That's why chlorine is in the 7th column of the periodic table. When they come together to form a diatomic chlorine molecule, they share 2 of the electrons. So now each atom has 8 electrons in its valence shell. This sharing results in very strong bonds because neither atom wants to lose that shared electron, otherwise it becomes unstable. The result is that covalently bonded materials are some of the strongest materials we find in the universe. Covalent bonds consist of something called directionality, or they have a property called directionality. Here's what that means. In methane, for example, the carbon atom in the center of the molecule is surrounded by 4 hydrogen atoms out at each corner. Now those hydrogen atoms each have a positive charge or dipole on the end of them, because they're sharing their 1 electron along the bond. So the positive charge is shifted out to the end. Well, you know that like charges repel each other. So therefore, the hydrogen atoms all repel and try to spread out as far as possible in 3-dimensional space. And the angle that allows them to spread out the most is 109.5 degrees. This property where the atoms spread themselves out as far as possible is called bond directionality. And it has some really important properties or results. First of all, because of the bond directionality, the positions of the atoms is extremely hard to change. A good example of this is diamond. Because it's hard to change the position of the atoms, the material will have very low ductility. It will be very brittle. So materials with covalent bonds, a lot of ceramics and diamond as examples, tend to be very brittle. In addition to that, the electrons are shared between the atoms, so there's no free electrons available to conduct electricity. The result is that covalently bonded materials like diamond have low conductivity compared to metals. Also due to bond directionality, the atoms are forced into an open structure resulting in very low density. You can't pack the atoms together very tightly when they're forced to be spread out as much as possible. And as we said before, bond directionality makes it difficult for atoms to move past one another, resulting in a brittle material. Lastly, let's look at ionic bonds. Ionic bonds generally occur in materials consisting of 2 or more different elements, one of which is not a metal. And a lot of times, ionic bonded materials are found in ceramics. What happens is basically capitalism. One atom releases an electron and shares it with another electron, or transfers it is a better way of saying it. So for example, let's take sodium. Sodium has 1 electron in its outermost valence shell. That electron is transferred from the sodium atom, which has low electronegativity, to the chlorine atom, which has high electronegativity and desperately wants that extra electron. The result is that you get a sodium plus cation and a chlorine minus 1 anion. Now the chlorine atom becomes very large because it now has a full stable octet, and the sodium ion becomes slightly smaller because it loses its outermost shell of electrons. The result is that you get small sodium ions and large chlorine ions that bond together in alternating patterns in order to keep the charge of the overall crystal neutral. So this is what salt looks like at the atomic level. A chlorine ion, then a sodium ion, then a chlorine ion, then another sodium, and then a chlorine, and so on. The bonding is between the 2 oppositely charged atoms, the chlorine and the sodium. The bonding is not the transfer of the electrons. We know this because if we stuck this salt in water, we could dissociate the bonds. In other words, break up the bonds by putting water molecules in the way, and you'd still have chlorine and sodium ions present in the water. What are some properties of ionic bonds? Well, first of all, they have no directionality. Because you're just combining a positive and a negative charge together, they can be oriented in any angle you want. But the structures that result from these small cations and large anions tend to be very complicated and therefore require a lot of space. So the result is that ceramics have moderate to low densities, lower than metals, but usually higher than polymers. There are no free electrons in an ionic bond. Therefore, the materials have very low conductivity. And because the bonds are strong and you have alternating charge of ions, it's very hard to move the atoms from one position to another. The result is very low ductility. Another phenomenon can occur where a material will have mixed bonding. Mixed bonding means you have more than one kind of bond present. We're not going to worry about this too much, but it happens in all kinds of materials. For example, iron combines both metallic and covalent bonds, which means that iron has a lower density and a higher strength than it should have if it were just purely a metal or metallically bonded material. There are also things called intermetallic compounds like aluminum lithium and titanium aluminide, which are a mixture of metallic and ionic bonds. And many ceramics and semiconductors are a mix of both ionic and covalent bonding.